Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
All right. Well, thank you all for coming to Asim Rastogi's end of internship talk. Asim's been here for the last 3 months and has had a super productive summer working on safe TypeScript, which he's worked on pretty much for the whole year, actually, since last summer. And we've also spent some time this summer looking at secure multi-party computation. So Asim's had this sort of double-header sort of internship. He's going to tell you today about safe TypeScript, our type-safe version of the TypeScript compiler.
Okay, thanks, Nick. Good morning, everyone. Thanks for coming. My name is Asim Rastogi, and I'm a PhD student at University of Maryland, College Park, where I'm advised by Mike Hicks. So I'm going to talk about, as Nick said, about safe TypeScript, which is joint work, of course, with Nikhil Swami. Okay, so TypeScript. It's a language from Microsoft, and the goal is to improve the state of the art in JavaScript programming. It's a gradually typed superset of JavaScript, and just putting some quotes from the TypeScript website, it gives strong tools for large applications, such as static checking, symbol-based navigation, auto-completion, refactoring, and so on. It provides classes, modules, and interfaces to help you build robust components, and it compiles to simple JavaScript. And compared to current JavaScript programming, this is a great leap forward. So if you're still writing JavaScript code, I would strongly recommend you using TypeScript. Okay, but typing JavaScript is in a way hard because it has so many dynamic programming idioms that having a sound type system is hard. So TypeScript, like its counterparts Start and Closure, intentionally gives up on type soundness. What that means is when the code is compiled to JavaScript, all the types from the program are uniformly erased. And that leads to unsoundness because, for example, downcasts are unchecked at runtime. This unsound type erasure has some benefits. You get very lightweight code generation. So the produced JavaScript is readable. It's in one-to-one correspondence with the source TypeScript that you write. Since there are no runtime checks, the performance is identical to what it would have been had you written plain JavaScript. And finally, types do not get in the way of good programmers. So if you're a good programmer, you can get around the type system and if you know what you're doing. But this unsound type erasure comes at some cost. And the cost is that TypeScript components are not robust. Okay, so let's make it a bit concrete on what I mean by TypeScript components are not robust. Let's say I'm a service provider. I have some variable x, which encapsulates a state, which is, let's say, an array of numbers. There is an index, which is the current index into the array, and index is a number. And it has a method next, through which I expect my clients to navigate through this array. So next just returns whatever is the current index and increments the index. And as a service provider, my expectation is that clients will only use this variable x at the interface of this iterator. So I define an interface iterator. It's a generic interface, which has a method next. And I call the client with this x variable of mine only if clients have this expected type. And then my expectation from this robust interface is that clients will respect my abstraction. But is it possible in TypeScript? Well, unfortunately, no. So here's a client code which has the correct type. It takes an iterator to number. But in the body, it just writes a dynamic field index and assigns it to true, thereby breaking the abstraction. Now, this is a well-typed TypeScript program. Types are erased uniformly. It compiles to JavaScript, and there's a type safety violation because I expected the clients to use only at iterator interface, but they can write dynamic properties. But not only this, in fact, I want a stronger guarantee. I want that client should not be even able to see my index field. So even if it writes a number to index, I want even that to be prohibited because I explicitly said that you should only use my next method and not muck around with the index at all. So as expected from a robust interface, I would like clients to not even access my index field. And this is an abstraction violation. And in TypeScript, it's not possible to do so currently. Okay, so in this talk, I present safe TypeScript, which is a sound and efficient gradual type system for TypeScript. We demonstrate that, contrary to the popular belief, soundness and efficiency is achievable for idiomatic TypeScript. The sound typing in safe TypeScript comes with advantages. For example, it helps you find type errors early. So we compiled the TypeScript compiler with safe TypeScript and found 478 static type errors. We found one functional correctness bug in Navier-Stokes, which is a heavily used and heavily tested Octane benchmark, but still this bug was latent and safe TypeScript found it. And another benefit of sound typing is that you get provably robust components, as opposed to what we just saw. But sound typing comes with its cost. And the cost, for one, is the runtime performance penalty. Since we have to check all the downcasts at runtime, we have to instrument the dynamically typed code, there is a runtime performance penalty for soundness. And the penalty is, so we compiled 118,000 lines of code using safe TypeScript, which was spread across 8 applications. And the performance overhead ranged from 6% to 3x. Now more details on this will follow later in the talk. Another cost of sound typing is that the programmer needs to understand some subtle corners of JavaScript semantics, and he needs to know how a type system works. So it's a trade-off. Okay, so how is safe TypeScript implemented? So this is the usual TypeScript workflow. The programmer writes an application, app.ts, invokes the TypeScript compiler using tsc app.ts. The compiler does syntactic checking, does some type inference and some lightweight type checking, provides some basic diagnostics, and finally emits the JavaScript code. Safe TypeScript is fully integrated into the TypeScript compiler, currently in version 0.9.5. Programmer can invoke safe TypeScript using this one compiler flag --safe to the TypeScript compiler. So programmer can enable or disable using this compiler flag. And our type checker runs post TypeScript type inference and provides stricter static checks, and moreover embeds residual checks in the emitted JavaScript code. So the kind of static diagnostics that our type checker does are inconsistent subtyping, implicit downcast, variable scoping, unsafe uses of this, and so on. Okay, so in next 15-20 minutes, I'm going to walk you through some highlights of our type system and show how safe TypeScript enforces soundness. So safe TypeScript type system is object-oriented, as with the TypeScript type system. But in contrast to TypeScript, which is purely structural, safe TypeScript distinguishes between nominal classes and structural interfaces to match the JavaScript semantics of classes. Okay, so let's take an example. So let's define a point interface which has two fields x and y, both of type number. We have point class, which again has two public members x and y, again both of type number. We write a function f that expects an argument of type point class, and inside the body it's going to assert that the argument that it receives is indeed of type point class by doing p instance of point c. So I didn't say it earlier, but I'm using this function assert whose semantics is that on false it just dies, and if it's true then it just returns void. Okay, so let's say we call this function f with a structural record with fields x0 and y0. Now as you may notice, with this call the assertion inside the function is going to fail because this is not an instance of point class. But for TypeScript, this is a WellType program because classes can be converted to structures, structures can be converted to classes, and therefore TypeScript will say it's a WellType program, it will go on, but my assertion will fail at runtime. In safe TypeScript, however, classes are treated nominally. So what that means is you cannot convert structures to classes, and therefore in safe TypeScript, at this point in the code, you'll get a static type error saying that the structural type x and y, x number, y number is not a subtype of point class, thereby preventing the assertion violation at compile time. On the other hand, if you called f by creating a new class instance, this will be okay with safe TypeScript. Okay, so now let's modify the example a bit. Let's say our function f, instead of taking point class, takes point interface. But we still call f with new point class. Now this is also okay with safe TypeScript because it allows classes to be converted to structures. So you cannot go the other way, you cannot convert class structures to classes, but you can always treat classes structurally using this subtyping provided by safe TypeScript. So point class is a subtype of point interface. Okay, so next we are going to see how safe TypeScript instruments the dynamically typed code in order to ensure type safety in that part of the code. So with our point interface and point class as before, let's define a function f that takes an argument p of type any, and it just writes a property x with string boom. Now there is a caller function g that expects a point interface. It calls f and then asserts that the type of field x must be a number. As you can probably see, this code is going to fail the assertion, but for TypeScript this is a well-typed code. And again, this code the assertion is going to be violated at runtime. So instead, what safe TypeScript does, as a first step towards enforcing type safety in the dynamic code, it tags the values when they pass from statically typed code to the dynamically typed code. So the compilation of function g before calling f is going to shallow tag p with point interface. We'll see how these tags are used later on, but for now the key thing to notice is that before calling f, it instruments a call to function shallow tag, which is implemented by our runtime library. Okay, now this function shallow tag, it's a very simple function. It just takes the type whatever you give it and just combines it with the current RTTI. So the current RTTI of p may be nothing, in which case it's just going to add point interface to the RTTI of the object. Okay, so now let's see how these tags are used. So now we'll look at the compilation of function f. All the writes in the dynamically typed code are instrumented with another runtime function called write, which is also provided by safe TypeScript runtime library. And this write function is going to enforce that when you write a field, you're always going to respect the invariants of the object. So in this case, what that means is, when you write, we are going to look at p's RTTI. We'll see in that RTTI what does p expect for field x, and then we'll see if the value boom respects that type. So since p's RTTI, because of this shallow tag, is going to be point interface, field x of point interface is a type number. So this will check if boom string is of type number, which it's not, so it's going to fail. And we catch the type error early. Okay, so classes are treated a bit special in safe TypeScript in that the tagging operations on the classes are optimized. So let's modify our previous example slightly. Instead of point interface, let's say the g function is point class, and it similarly the function f remains same, and we call f and then assert again. In this case, when this code is compiled, there is no tag. Safe TypeScript inserts no tagging operation for p. But earlier, as you saw, there was a shallow tag for point interface. And why is there no tagging? Because classes have primitive tags provided by the JavaScript semantics. When classes are compiled to JavaScript, they have a prototype field where the prototype field points to the class that they are instance of, and that gives us the RTTI, so we need not add our own RTTI. So class instances have primitive RTTI, no tagging, so you get efficiency if you are using more classes. Okay, so this was what happens when values flow from statically typed code to dynamically typed code. Now we are going to see what happens when values flow the other way around, when dynamically typed code passes values to the statically typed code and they are used via downcast. So we have a function f which takes p, which is of type point interface, and it asserts that whatever it got is actually has actually a field x which is of type number. But here is a dynamic caller g which has p of type any, and then it calls function f but performs a downcast on p before passing it to f. And then this is a caller of g which has in its x field a string. So in TypeScript, it's going to erase all the types, it's going to erase all the casts, and therefore, as you can see, this assertion is going to fail at runtime because x is value boom, which is a string, and it's not type number, it's type string. In safe TypeScript, however, the downcasts are not erased completely, but downcasts are checked at runtime. So when this function g is compiled, the call to f is actually, it inserts a call check that p is of type point I. And this check function is again a safe TypeScript runtime library function. It's going to say that, okay, you're checking for p's conformance to point I, so p should have a field x of type number, it should have a field y of type number. If it does, I'll add point I to the tag and return O, otherwise I'll raise a type error. So thereby we catch the assertion violation early in the code. So all the downcasts are checked in safe TypeScript. Okay, as with the tagging operations, even
Question in the middle.
oh yeah, definitely.
Can you go back a step?
Yeah, please feel free to ask questions.
So you have you're passing in the object literal that matches the shape of point I, but before you said point I was nominally subtyped instead of structurally subtyped, and then your assertion over here checks structurally instead of nominally.
Point class was
Point C was
Point C.
So point C was the class, point I was the interface.
Oh, I guess.
Yeah, point I is the interface and point C.
So if you did not have the cast, would you still
This
call
test?
check at the point I cast?
You
Would
mean this
still,
test?
Sorry, I can't see.
The
No, the
one
cast
down.
in TypeScript, in function G rather.
The point I cast.
Oh, the point
Yeah,
I cast.
If you did
I
not
think
have
in,
that.
in that case, TypeScript would give you an error because it won't. But we will check still. I mean, even if it doesn't,
So you'll still check.
we'll still check.
Okay.
Yes, yes.
So you said that you have a safe write function that's in some previous slide. You have the function write, and you said this is the safe version of the assignment.
Uh-huh.
Does this mean that all the assignments are unsafe? And you have to explicitly use the write function?
So if you have an assignment in the dynamic part of the code, then it's going to be instrumented with this write. It does not necessarily mean that it's unsafe. So for example, you could have written a number over here, in which case write would have succeeded.
So the write function is asserted like automatically.
The compiler, the safe TypeScript compiler instruments the code to insert these write every time you write a field in the dynamic annotated code.
The right-hand side of the slides is generated code by the compiler.
In the first example where you had the index and the client was actually updating index directly, what was the check that prevented that from happening?
I'll tell you about that.
Oh, okay. Okay.
I'll revisit those examples towards the end of the talk.
Okay.
So in your check function, if instead of casting to point I was casting to point C,
Uh-huh.
then your implementation of the check function just compares structure, right?
No, I'll talk
So you
about
have
this
two
now.
different checks.
We have check depending on what's the target type. So
Okay.
let's see, that's the next thing. So yeah, it's a good segue. So let's say instead of point I was downcasting it to point C, but as happens with the tagging, even downcasts are optimized for classes. So now, instead of checking it structurally, I can just do JavaScript native instance of check. So I don't need to do structural checks. I can just call JavaScript native instance of, and this is very fast, much optimized, and so on.
So TypeScript doesn't do that runtime check by default?
No.
Do you know why they chose not to do that?
I can answer if you want. So TypeScript really, the philosophy there is erasable type system and leaving the JavaScript as vanilla as possible. Like the moniker is like the kind of JavaScript you would have written by hand. And I think any kind of runtime checks, any kind of inserting that in, you would have to be then doing all the work to pull them back out again to get back to that point. Instead, we give you a design time experience where you can get IntelliSense, you can get a lot of good error checking, but maybe not all of the error checking is field work and whatnot.
And again, you would do this without the cast as well.
Yes. Any other questions? Okay. Right. So now comes the part. So we have seen that when going from statically typed code to dynamically typed code, we inserted tags on the objects. But safe TypeScript is even smarter. It's going to add minimum amount of tags that are needed to ensure type safety. And in addition, we are going to provide programmers a way to get around the tagging behavior. So if the programmer says that I'm willing to use this type system at a much stricter mode, I don't need any tagging behavior, programmer has a way to say that. So that's what I'm going to talk about next. Okay, so let's extend our example a bit. So instead of so we had a point I before, which was an interface with X and Y fields. Let's write another interface which is 3D point I, which is a 3D point, and it adds a field Z of type number to the interface. We have these small functions f, g, and h, so the function main takes as argument a 3D point I, it calls h takes an argument a 3D point I, calls g takes an argument a point I, calls f, and f takes any. So as you can see, going from bottom to top, the precision in the type is decreasing. So how is this compiled in safe TypeScript? There will be some tagging involved, but how does the tagging work? Okay, so when you compile f, there is no tagging.
Main.
I'm sorry, main, yeah. Thanks. So when you compile main, there is no tagging. And the reason is that there is no loss in precision in the argument type. I have a 3D point I, the callee expects a 3D point I, so I'm just going to call the function. When you compile h, there is a loss in precision because I have a 3D point I, but the other guy expects a 2D point I, so there is a loss in precision of field z, and safe TypeScript is then just going to add only the field z on the tag. So we call this differential tagging. So you only add parts of the type that are being lost in precision rather than the complete type. So you just add the field z and that's it. Okay, now when you compile function g, there's a complete loss in precision. You're going from point interface to any, and so you need to add to the tag point interface. So these tags evolve at runtime. So at this point, the tag will be maybe nothing. At this point, the tag will be z colon number. At this point, it's again going to become a 3D point I. And again, the shallow tag just takes the existing tag, combines it with the type that you give it, and resets the tag.
So that record, z colon number, and the one above it, point I, what exactly are those that you're passing?
So those are runtime representation of types.
Okay.
So safe TypeScript compiles types into the emitted JavaScript program, and types have some runtime representation like objects. So we have a type class, we have a different instances of the class, and so on.
For each type, you
Yes.
actually emit
A type representation.
a type representation
Yes.
as well.
Yes.
We'll see it in the demo.
Yeah, we'll see it in the demo.
Okay. Okay.
Okay, right, and function f will be compiled like we don't care. Okay, so, but this is a bit unfortunate. I mean, if you're going to say that the compiler is always going to emit tags no matter whatsoever, then programmer has no flexibility to say that I don't want this tagging operation, there's a performance overhead and I want to avoid that. So then safe TypeScript provides programmers a way to adhere to a stricter type discipline but avoid tagging. So we provide a new operator called erase types. The semantics of erase types is that a value of type erase t is known to be a t statically, but it may not have a runtime type tag at runtime. It may not have a type tag at runtime. And if programmer writes these erase types in the program, he has to conform to a more strict discipline, which we'll see in the next slide. But all the erase types are erased from the output. So we were compiling these normal types into the JavaScript output, but erase types will be erased just like what TypeScript does with all the types. Okay, so how does programmer say that sometimes some type should be erased? So this is how programmer says it. So let's say programmer wants the point interface to be erasable. So he says, okay, extend erased. Erased is an empty interface provided by the safe TypeScript compiler, and it's just to indicate that this interface should be marked erased and so on. Okay, we have the 3D point as before, and now let's see how the compilation of this looks like. So when this code is compiled, there is no tagging involved in this code. Specifically in function h, we were losing precision going from 3D point I to point I, but it just compiles as is. Previously it was a shallow tag, but now no tagging despite the loss in precision, and the reason is that your target type is a erase type. So the compiler knows that it's not going to be used dynamically because it will be erased, so I need not tag it. On the other hand, in function G, we are passing an erase type to dynamic context, and that's a static type error. So safe TypeScript does not allow you to program dynamically with the erase types, because recall that they may not have an RTTI at runtime. We cannot enforce the invariants, therefore you have to use them only statically. So this is a static type error, and you cannot pass erase types to dynamic context. Okay, so now we revisit the robust component example. So this was our first example in which.
So I mean, couldn't you have allowed that one, but then that is passing the 3D point I to the point I, and then just made sure that there was no other downcast from on the other side where we were passing it to.
That's what we did. So we allowed 3D point I to go to point I.
The static type error is where?
This is in G part of the code. When you give a point I to any, that's a static type error. But we did allow 3D point I to go to point I, and it compiled as is. There was no tagging involved. But if you try to provide point I to the dynamic context, that's a static type error.
You also,
one step away.
and you also wouldn't be able to downcast from point I to 3D point I, right?
No.
So, and you also wouldn't be able to index like inside G, to index into it with a Z.
Exactly. No, you cannot.
Right.
Good point. Yeah. Yeah, because point I is an erase type. All we know that it has X and Y. We don't know anything about it. At runtime, it may not have an RTTI. So that's it. You need to adhere to a stricter type discipline, and only then we can guarantee the erase property of erase types. Right, so revisiting our robust components example, this was our first example in which the client was trying to write index to a Boolean value true, which was bad, but now safe TypeScript provides robustness by a type soundness theorem. So at runtime, this is going to be a type error, and safe TypeScript gives you formal guarantees for that. So there are several useful results that come out of type soundness theorem, one of which is the runtime type tags that you add, they always remain consistent with the object. So if I say that the tag has a field f type number, then the object has a field f and it contains number in it. Safe TypeScript invariants always ensure that. And that the tags evolve in the subtyping hierarchy. So the tags just not are some ad hoc tags, they always become more and more precise in the subtyping hierarchy. And our full formalization and proofs are in the associated technical report. Okay, so now this is the more interesting example, right? In this case, we want even this to be disallowed. Now this is basically type safe in the sense that the client is writing a number to it, but we don't want even this to happen because index is my private field. I don't want to expose index to you. Okay, so how can programmer achieve this? So programmer can make iterator to be an erase type. So he says, hey, the interface iterator A extends the erased interface, and this is going to ensure that this is not a well-typed code anymore. So this will be a static error because you're trying to take it to any, and this way you can get stronger abstraction properties from erase types.
So opaque types, is erase the same as opaque, or is there some sort of, why did you choose, I guess you know, the idea of hiding abstractions, right? You know, by saying you can't do anything inside the box.
Right.
It's
so
been around, yeah. Okay.
Yeah.
So is it the same? I guess.
So it's, I mean, in a lot of ways, erase types are like you would expect types to behave in most languages, right? The types are often erased in, say, in a language like ML, let's say,
Okay.
and you have to respect the invariance of, you know, of the only way you can use a value is by the published interface of.
Okay.
And that's what this is allowing you to do.
Okay. So it's just what other languages have anyway.
Mhm.
You
In a
know,
way,
Language
right, but
types.
the interesting thing here is that it's a partial erasure modality. Like you don't systematically erase everything, you get to decide exactly what is erased and what is not erased. And it's not quite the same as opaque types, because here, the iterator, it's saying that it has a next field. It's not completely abstract.
Right, I see.
So you're revealing that this is the interface I publish, and that's all you can use.
Right, so we have an abstraction theorem for arrays types as well. It's in our technical report again. Okay, so this finishes the overview of safe TypeScript type system. There are many more features in safe TypeScript. We have support for generics, we have support for arrays, and we support covariant subtyping of arrays in a way by having mutability controls. We support sound overriding, inheritance, and so on. And all these features help us scale our safe TypeScript to large TypeScript applications. Okay, so some experience with TypeScript. Yeah.
Okay, you first.
Oh, no. I was just looking at the list, and one of the gotchas with a lot of JavaScript programmers is the this pointer
Yes.
and how flexible and dynamic that thing is.
We did not add this pointer here, but safe TypeScript enforces that you use this pointer in a sound manner. And I mean, a short introduction is that it treats methods and functions differently. So, for example, we will not allow you to project a method. So if you write a method and you use this parameter in that, we won't allow you to project a method out of the object because this will be bind dynamically to something else. So safe TypeScript enforces that you use this in a sound manner. Does that answer your question?
Yeah, I have to think about that for a second.
Okay, we can talk about it later.
So how big is the language manual for safe TypeScript? How much does it extend the TypeScript manual?
We don't. It's all implemented in the TypeScript.
Well, I mean, it's a language, right? So it has features, and the question is, how long does it take to tell people all the features that you provide? I mean, obviously, erased is one part of it, but
Yeah.
You're talking about mutability controls. What exactly is that?
Yeah. So I mean, there is some learning involved. So mutability is basically in TypeScript code. It allows arrays covariant subtyping, which is unsound, but it's a useful idiom. So we provide you covariant subtyping of arrays, provided that the target is a read-only array. So you can go from 3D point array to a point array, but that point array, the target point array should be immutable because otherwise it's not sound. So we have these many things like that which are to support the popular idioms like this. But I don't know how much time will it take.
Our technical report is it formalizes a large part of this type system, and it's larger than any known formalization of TypeScript. So formalizing the whole thing is, a huge effort. Probably not one.
I'm not talking about the formalization. I'm more interested in. I'm a programmer that knows TypeScript, and I want to use this. How many pages of text do I have to read until I understand all the things that are necessary to use it?
Right. It's a good question. I mean, 12 pages of a bubble paper at this point.
That's pretty good.
I mean,
I don't know. Maybe you just look at our samples.
Yeah, you can just read the implementation section. You can just read the implementation section and still know a lot. I mean, you don't have to read the formalization to understand safe TypeScript.
Oh, sorry, one other question. Do you treat properties and indexers invariantly or covariantly?
Invariantly.
Invariant, okay.
Because they are mutable, so it's unsound to treat them covariantly. You have a question? That's okay. So experience with safe TypeScript. So we bootstrapped the safe TypeScript compiler. It's about 90,000 lines of code with 80,000 lines of TypeScript compiler code and 10,000 lines of code written by us. The compiler is it's implemented in version 0.9.5, and that compiler code base is heavily class-based, which is good for us because then the performance overhead will be minimal, as we saw. Most of the code is carefully type annotated. It's written quite well, I would say. We found 478 static type errors. which are classified as follows. So 98 uses of covariant and contravariant subtyping, 130 uses of covariant method argument subtyping, 128 cases of variable scoping, 52 cases of projecting a method and leading to a potential unsound use of this, and so on. We fixed all those errors, and then we found 26 failed downcasts as well when we ran the compiler, and out of which 5 were in the code that we wrote. So, I mean, without tool support, I think it's very hard to write a sound code.
So, like, I know those runtime errors, they were actual bugs, or they were problems with type violations?
They were type safety violations, but like we did not have a example where that would have yielded to some bug. But these were type safety violations where you make some downcast, the downcast was not sound, but it so happened that you didn't end up using the variable later on in the code.
You might have been doing some kind of ancillary check. An ancillary check gave you an invariant that you knew, okay, once I know this invariant, I can make the downcast.
Or you did the downcast, it succeeded silently, you projected a field that didn't exist, but that undefined vaporized into a boolean at some point, and it worked anyway.
It's JavaScript.
So when you say bivariant array subtyping, you just said that arrays were allowed to be covariant in safe TypeScript. So how would you have caught?
So they are allowed to be covariant if the target arrays are immutable, but in TypeScript there is no such notion. So we had to add a mutability support for the, yes. Okay, so the runtime overhead of type safety in this experiment was only 15%, which is quite good, I would say. And it's mainly attributed to the fact that most of the code was class-based. So the downcast checks were very cheap because we could do instance of, and tagging was just no op. Okay, so we also compiled the latest TypeScript code, version 1.1, with our compiler. That's a much smaller code base. It's 18,000 lines of code as opposed to 80,000 lines of code previously. But there is a design paradigm shift. Instead of heavily class-based, the code is now heavily interface-based. So this gave us like the other end of the spectrum. And so we found 81 total static type errors, out of which, so mainly they were variable scoping and array subtyping. But the runtime overhead now increased to 3 times, and it's because interface checking and tagging is costly.
That's new version of TypeScript?
Yeah.
Oh, and it's 4 times smaller?
I think it's a pre-release version, but yeah.
Yeah.
That's it.
I mean, part of it is that the compiler leading up to 1.0 kept changing because the language, we kept mucking with the language and changing it. So it kept getting bloated and bloated because of the code that was left behind. And then we decided, okay, let's actually start from scratch and first principles, but we already know, and we've got a language that's changing so much, and then built something from there. We built a much lighter weight compiler.
Okay, so as I said, the high overhead is because of more structural types. But having said that, I would also say that we did this experiment in last 2 weeks. So we did not optimize our runtime library for interfaces much. So there may be avenues for more optimization there. Okay, the third experiment we did was we used Octane, the standard Octane benchmarks. That's a total of 10,000 lines of code. We found one variable scoping bug in Navier-Stokes, which is a heavily tested and heavily used benchmark, but we found this bug, which yields to functional incorrectness. So for these benchmarks, there was high runtime overhead if you don't have any type annotations, and the overhead ranged from 2.4 times in Splay to 72 times in Crypto, and average of 22 times. But once you start adding type annotations to these benchmarks, you recover the performance. And for the type benchmarks, the average overhead was just 6.5%.
How many annotations did you have to write?
It's in the paper, but I don't have the numbers here.
So it starts, it's just pure JavaScript?
Yeah, it starts at pure JavaScript, and then we add annotations to it to make it typed, and this is what the performance goes.
I mean, it's interesting in some sense. Many of these benchmarks kind of came to Octane from languages like Smalltalk,
Right.
where they started out life as typed programs, they became untyped, and now we're sort of making them typed again.
Okay, so now let's see a small demo. So this is the safe TypeScript playground. So I have interface point I have interface point class. There's a function h, which is writing x.x to boom. There's a function f, which is point interface, and then g, which has 3 numbers, just like 3D point interface. Okay, so this is what the first thing happens. We register types. So this comes to your question, what the type representation is. So it's registering a point I interface and saying that it has a x field, which is of type number, y field of type number, and some other things. This is the class compilation, and this is the registration of the class with the runtime system, and so on. So if we see below, we see the incremental tagging here. So we have x, y, and z. Point I is just x and y. So the shallow tag in this case is just for the z colon number. When you go from point I to any, you tag it with the interface type point. And finally, the right in the dynamically typed code is instrumented by using right field. Okay, so now let's see. Let's try to modify this to use a point class. And I'll just recompile it. I don't know how good the dynamic thing works. It worked, okay. Anyway, so once you annotate it to be a class, you note that the tagging disappears. So there's no tagging anymore because tags for classes are free. So when you go from f to h, there's no tagging. Moreover, this guy now has to be check and tag to the class type. So recall that structures are not convertible to classes, so we have to insert a runtime check. And depending on how this guy started its life, this check is either going to fail or succeed. Okay, so now let's make this a point interface, but let's make this guy erase. So we call it virtual in our implementation. So this is how you say that an interface should be erased. And if you'll have to recompile it. So if you recompile it, then you should see that, right. So now at this point, the tagging disappears. Earlier we were tagging with field z, but now since point I is erased, this just goes through as it is. But at this point, we get a static type error, which is that you cannot pass any argument to, you cannot pass erased arguments to context any. So this is a type error, and safe TypeScript emits with this unsafe annotation, and you can give some semantics to unsafe, whatever you like. Okay, so limitations and work in progress. So we currently do not have eval and other unsafe constructs of the language in safe TypeScript, but we know how to add them, and this is some work that we did last summer on giving this eval and other unsafe constructs an adversarial type. So we explored on how you can have unsafe JavaScript and still interact with it in a sound manner. So we think that same ideas can be used even in this case. Some implementation limitations. So as I said, it's implemented in version 0.9.5, but we currently do not support external modules. We only support internal modules, and that the TypeScript compiler has now moved on to v1.1, and we are having ongoing discussions on how to integrate our safe TypeScript with the TypeScript compiler version 1.1. Okay, so that's the end of my talk. So I talked about safe TypeScript. Feel free to download it. It's available on this link for download. We submitted a POPL paper on this with our theorems and lemmas and whatnot, and the submitted paper is here. We have a full technical report which contains our formalization of a large core of safe TypeScript and complete proofs, and here's the online playground which I just showed you during the demo. So thank you.
I had a quick question on sort of the overhead you're talking about, right? It seems like there are two parts. One is just you have to do the tag checks, but the other is the particular, I mean, you're encoding all the type information in JavaScript itself, right? And so that seems like just pushing all of that type stuff in JavaScript could be pretty expensive. I was wondering if you knew of a sort of a rough breakdown of what was the cost of just having the conditional check versus the cost of managing all the type information. And then sort of the follow-on is, I mean, would it be useful to push that type information into the actual JavaScript runtime? You know, it might be a lot more efficient to represent there, and it might actually be useful to the runtime as far as its code gen and execution.
Definitely. So I'll answer the second part first.
Sure.
So it's going to be more efficient. And in fact, if you have the option of modifying the runtime, then you can even make use of soundness of safe TypeScript to, for example, do away with the checks that JavaScript virtual machine already does. So if you have x plus y, in the source types, we know that x is a number, y is a number, so we can just add them without doing all the case analysis in the JavaScript virtual machine. So if you have the option, you can definitely optimize much more. For your first question, I think the cost of translating types is one-time cost. It just happens during.
Well, but I guess when you're doing a comparison, you know, I have type X and I have type Y. Like if you're representing them as strings or something,
Yeah.
you know, you're doing a lot of stuff there. Right? So
Yeah.
I'm sort of wondering, like,
So we try to be careful about using a lot of sharing. So the same type is going to appear many times in the program, and we'll try to use reference equality for them as much as possible.
Okay.
We try to use nominal types as much as possible. If a type is nominal, we're going to do a nominal check as opposed to a structural check.
We have caching of, for example, if you have an interface and you want to check if some object complies to that interface, we go to the structure of interface and we cache all the structural representations also. So we have tried to optimize it, but then at some point for structural types, you have to go through each field and do these expensive checks.
okay.
But I don't think we have a breakdown on just that, because checks in a way involve traversing a type. So I don't know how we can separate cost of just the checks versus traversing the type.
Well, I guess I was thinking that the traversal part versus just the if branch, right? I mean, you always have to say if the type and do a little fall through there.
see.
And then there's the other cost, which is actually, you know, traversing the type information or how you do the actual resolution of that.
Yeah. Okay.
And one of those you kind of always have to pay, right? You always have to do the if check.
Right.
The other one can be optimized more or less depending on
Yeah.
what representations you have.
I mean, I guess the other thing is that it's nice to generate code that's just ECMAScript 5 compliant.
Right. Changing the engine.
Changing the engine would be great, but would also scope down its usability.
So I also have two questions. So with your instance of checks for the classes, how does that deal with inheritance and base classes? If I say I have a derived and I want to check instance of base, so how does that work with that?
So when this inheritance is compiled by TypeScript, it's going to maintain the prototype. So the base is going to eventually appear in the prototype chain of the derived instance. So the instance of check will work, and we'll use the instance of check
Okay,
itself.
it'll just piggyback on the
Yes, it will just
extent.
piggyback on the
Gotcha.
JavaScript
Okay.
instance of check.
And my second question is, you showed kind of properties. So how does the RTTI work with signatures and overloads? That
Right.
might be a very big question.
Right. So if you have methods in the type, then those methods are also put in the RTTI. And if you call those methods dynamically, we will do dynamic type checking for arguments and for return type and so on.
Including like loose signatures in an interface.
You mean like overloads?
Yeah, but without, like, not methods, but loose signatures. So I have an interface I that is callable in various
Yeah.
ways.
We support that too.
Yeah.
So, the way, for those of you not TypeScript experts, correct me if I'm wrong on this one. So the way TypeScript supports overloading is that you get to write, you have an implementation of a function, and then you get to supply multiple signatures for that function that need not be related by subtyping to the implementation signature. So they can just be, I can write a function that's a number-to-number function and then claim it has type any-to-any also, and that would be fine.
They do have to be related by subtype, but it's our very
But it's your
loose
weak notion of subtyping, right? So, so for soundness, what we do is we say, okay, what goes into the RTTI is the implementation signature only. And if during type checking, we will piggyback on your type inference results to resolve to the overload that TypeScript chooses. But at runtime, we will check against the implementation signature, which is the only true, the only sound signature in some sense. Does that answer your question?
Yeah, part of it. There's also the case where you have no implementation.
Yes. So when you have no implementation, then what you can do is to go, so we do this, so the TypeScript programs are all typed with respect to this library that gives types to the JavaScript environment. It's like a 15,000 line spec. So we implicitly treat every type declaration in lib.d.ts as an erased type. Meaning that you can, some external library is claiming that it provides to you a function that behaves both like an any-to-any function as well as a number-to-number function. And you're willing to trust that, you know, array.splice behaves in this kind of ad hoc polymorphic way. And then since it's erased, there's no runtime representation for it. And as long as you call array.splice on a value where the receiver has static type array, we will just resolve it the way the TypeScript compiler resolves it, and there's no runtime check.
So if I declare an interface in my own code, though,
Yeah, and then you can mark that interface as
That's
erased,
it.
and you can just use it. But you would have to then respect the static typing discipline for that particular, for values of that interface.
I see.
So that's how we support lib.d.ts. So we mark all the specification in lib.d.ts to be erased so that we don't add tags to things that are not ours.
Other questions? All right, let's thank Asim.
Thank you.